This is a quick video tutorial on platelets and their formation and function. We are going to start with an overview of their origins and then provide a highlighted look at the components of hemostasis. Platelet formation is regulated by the hormone thrombopoietin, with the final result being a megakaryocyte. When formed, the megakaryocyte presses up against a sinusoid, a special type of capillary in the marrow, and sends cytoplasmic extensions through the sinusoid wall into the bloodstream. These extensions rupture, releasing the platelet fragments like stamps being torn from a sheet of postage stamps and seeding the blood with platelets. The plasma membranes associated with each fragment quickly seal around the cytoplasm to form tiny, grainy, rough disc platelets. Each cubic millimeter of blood contains 150,000 to 400,000 of the tiny platelets. The homeostasis response, which is fast, localized, and carefully controlled, involves many blood coagulation factors, normally present in the plasma, as well as some substances that are released by platelets in injured tissue cells. During the hemostasis, three phases occur rapidly in a rapid sequence: vascular spasm, platelet plug formation, and coagulation or blood clotting. Platelets play a key role in hemostasis by forming a plug that temporarily seals the break in the vessel wall. They also help to orchestrate subsequent events that lead to blood clot formation. As a rule, platelets do not stick to each other or to the smooth endothelial lining of blood vessels. However, the endothelium is damaged and underlying collagen fibers are exposed. Platelets, with the help of large plasma proteins called von Willebrand factors synthesized by endothelial cells, adhere tenaciously to the collagen fibers and undergo some remarkable changes. They swell, form spike processes, and become sticky. Once attached, the platelets are activated by the enzyme thrombin, and their granules begin to break down and release several chemicals. Some, like serotonin, enhance the vascular spasm. Others, like adenosine diphosphate, are potential aggregates and agents that attract more platelets to the area and cause them to release their contents. Thromboxane, A2, a short-lived prostaglandin derivative, that is generated and released, stimulates both events. Thus, a positive feedback cycle that activates and attracts greater and greater number of platelets to the area begins, and within 1 minute, a platelet plug is built up, which further reduces blood loss. Platelet plugs are loosely knit, but when reinforced by fibrin threads to act as molecular glue for the aggregate platelets, they are quite effective in sealing the small tears in the blood vessels that occur with normal activity. Once the platelet plug is formed, the next stage, coagulation, comes into play. Coagulation, or blood clotting, during which blood is transformed from liquid to a gel, is a multi-step process that leads to its critically important last three phases: clot initiation, clot formation, and fibrinolysis. The complete coagulation process is much more complicated, however. Over 30 different substances are involved. Factors that enhance clot formation are called clotting factors or coagglutants. Although vitamin K is not directly involved in coagulation, this fat-soluble vitamin is required for the synthesis of 4 of the procoagulants made by the liver. Factors that inhibit clotting factors are called anticoagulants. Whether or not blood clots depend on a delicate balance between these two groups of factors. Normally, anticoagulants dominate the clotting and is prevented, but when a vessel is ruptured, procoagulants' activity in the area increase dramatically and clot formation begins. The procoagulants are numbered 1 through 13 according to the order of their discovery, hence the numerical order does not reflect the reaction sequence. Tissue factor 3, calcium, and factor 4 are usually indicated by their names rather by their numerals. Most of these factors are plasma proteins made by the liver that circulate in an inactive form in the blood until mobilized. Thrombin catalyzes the polymerization of fibrinogen. As the fibrinogen molecules are aligned into long hair-like insoluble fibrin strands, they glue the platelets together and make a web that forms the structural basis of the clot. In the presence of fibrin, plasma becomes gel-like and traps foreign elements that try to pass through it. In the presence of calcium ions, thrombin also activates Factor 13, a cross-link enzyme that binds the fibrin strands tightly together and strengthens and stabilizes the clot. Clot formation is normally complete within 3 to 6 minutes after blood vessel damage. Because extrinsic pathways involve fewer steps, it is more rapid than intrinsic pathways. In case of severe tissue damage, it can promote a clot formation within 15 seconds.